Okay, 3.2 Basic Differentiation Rules. So, in 3.1, we learned the definition of the derivative is f prime of x, or the derivative of f of x is equal to the limit of f of x plus delta x minus f of x all over delta x as delta x goes to 0. And you found out on the last test and homework assignments that it's really a lot of work. For instance, if I gave you the function x cubed, if I wanted you to find the slope of the tangent line, which is known as the derivative, when x is equal to 3. Okay, we'd have to go through this limit process. It's definitely takes a lot of time and takes a lot of work. This whole chapter, I'm going to show you shortcuts for derivatives, which is still, in some cases, very difficult, but it will definitely be easier than doing this process over and over and over again. Okay, the first shortcut rule we're going to use is the constant rule. The derivative of a constant function is 0. That is, if c is a real number, okay, so if c is any number between negative infinity and infinity, then the derivative, remember this means the derivative of the constant with respect to x would be 0. And the reason why here, like you don't even really need a proof to really understand this, if you have some constant function. So a constant function is some horizontal line. Let's say that this is f of x is equal to 3. Does it make sense that the slope of this line, okay, is going to be 0? So the slope of this line, no matter what x value you pick, it's going to be 0. So here, the slope of the tangent line lies right on top of the function. Okay, and I'll go through the proof. Okay, and this would be a proof that I would expect you to be able to reproduce on a test. Okay, so let's say that you have some constant function, f of x equals c, okay, and I want to use the definition of the derivative to prove that f prime of x, okay, when this is a constant function, is equal to 0. So this is what I'm trying to prove. Okay, so here, okay, let's say this is c, then this would be c plus delta x, or let's say that this is x, then this would be x plus delta x, where the distance between these two is delta x. And we'll say that this is equal to c. Okay, so we're just going to substitute in here. So now we know that f of c plus delta x is c, minus f of x is equal to c, all over delta x. Now we're going to continue to simplify this and then evaluate it. Well, we know c minus c is 0, and that's going to be divided by a delta x. No matter what delta x is, as long as it's not 0, which in this case it isn't, it's some distance between these two numbers, then 0 divided by delta x would be 0. I'm sorry, 0. Then if you take the limit of 0 as delta x goes to 0, that's going to be 0. So that is the proof of the constant function. Let's do some concrete examples now. Okay, so let's say that I ask you to find the derivative of y equals 7. So again, if we were going to graph y equals 7, y equals 7 would look like this. If I asked you to find the derivative, remember that's the same thing as find the slope. Okay, so the slope of this function, no matter which x value you point here, the slope of this function, which I'm going to say y prime, is going to be 0 because it's a constant function. Okay, let's look at B. What if I asked you f of x equals 0? Well, now this horizontal line would be right here. F of x equals 0. The slope of this function, no matter which point I pick, the slope of this function, f prime of x, would still be 0. S of t minus negative 3. Okay, hopefully you can see this is still a constant function. So the slope would be s prime of t would be equal to 0. Looking at D, we've got y equals k pi squared, where k is a constant. So k is a constant, pi is a constant. That's 3.14 squared. So it's still constant. A constant times a constant times a constant, still a constant. Okay, if we take the derivative of the constant, that is going to be 0.